Hello, everybody. We are the Toshiba team, and we worked on the storage benchmark workload analysis project as our senior design project. Our sponsor was Ken Allen, who's right in this third row right here. Hi, Ken. My name is Peter Zuppel.
Hi, Val.
So just a little background on who we worked with. Toshiba is a pioneer in designing electronic components, has been for years. They invented flash memory in 1987. We specifically worked with the Toshiba products, or storage products business unit, which heavily focuses on storage products. Big data collection, storage, and analysis has been increasing exponentially over the years. Storage devices are now expected to hold terabytes of data. That's pretty much the norm nowadays. Performance of these devices is very important for certain applications like cloud file systems and distributed file systems in general, cloud file systems. Toshiba is a vendor of hard disks and solid-state drives, and so they asked UCSC to give their thoughts on some design improvements and try to analyze certain things about the drives and what they're doing. So Toshiba wants better tools to analyze, filter, visualize, and manage their benchmark data. The tools they were previously using weren't very fast. They were using an unnamed spreadsheet program. And they wanted tools that could compute things faster, better, with more emphasis on more sophisticated analysis on the benchmark workload data. And the tools shouldn't be so sophisticated that it would take a rocket scientist to use them.
Okay. So the goal of this project was to take benchmark data and visualize them using hardware, like using modest hardware. The system should also be able to support benchmark data analysis, basically.
Our initial approach to the project was get the data file, parse the data file, and calculate the data. But the reality is, using a brute force computation of data will result in memory error, and runtime will take an impractical amount of time. So we have to develop specialized algorithms for each analysis.
So the first thing we had to do was actually conduct a literature review and then research ways of basically visualizing the data. After that, we would then look at how Toshiba returns their data from doing benchmark testing. And then looking at that data, we would then find ways of how to parse the data, grab key components that we need. And then putting it all together, we put it into a data visualization management system that basically that uses the specialized algorithms, multiple visualization library tools, and putting it all together in a graphical user interface.
So we've been talking a lot about benchmark workload data. Here's an example of it. As you can see, it consists of a row ID, which identifies the request. The runtime can also identify the request. It's the cumulative runtime of the benchmark at that point. So no two runtimes can be the same. We also looked at the start logical block address, the I/O request size, and whether the request was a read or write. This is just a small subset of the actual data. There could be potentially hundreds of thousands of entries. There was no real bound on the scalability of visualizations of the filters we used. So for the data analysis portion, we collected a bunch of different types of filters. We looked at the spatial temporal locality of the requests. That's kind of normal for this type of analysis. We also looked at the number of reuse distances and number of reads to a logical unit. We visualize these using heat maps, CDFs, scatter plots, line graphs, among others, bar graphs even. We ran into a few challenges actually with filtering and visualizing. With filtering, we had to kind of spread out the LBA. So we were given start LBA and an IO request size. We had to figure out all the addresses that a request was hitting, including, the addresses including an IO size. But not only with the filtering, there are also problems with visualizing as well. For instance, with the heat map, it's kind of hard to organize how to represent each address because there could be billions. So to actually make it make sense, you have to think about how you visualize it.
So there are 3 advantages using algorithms to compute the data sets. First, it could calculate scalable amount of data. And then second, the runtime efficiency will reduce the runtime into a more practical amount of time. And RAM efficiency, it could prevent RAM overuse while calculating the data.
This is the architecture of our visualization management system. As you can see at the top of the graphic there, we have a user interface which consists of a GUI and a command line interface. The user is able to send commands to the data manager, which basically just moves an input CSV file, comma separated value file, with the benchmark workload data, and moves it around to the database to store, the computation modules to filter, and the plotting modules to actually visualize. And that creates, those in conjunction creates those visualizations at the bottom. The architecture kind of has a modular design. You can add new filters, new visualizations, so it's very expandable. We cache the graphs in the database, so you don't actually have to, recompute if the graph is already in there. We used Python for all the modules, and we used Postgres SQL database for the database. Yeah.
To summarize our accomplishments, we researched literature and interpreted literature comparing different workload benchmarks in order to visualize and effectively reveal any patterns that arose in the data. Also, we optimized our algorithms in order to speed up the process of reading that CSV data in order to be scalable for large amounts of data, maybe larger than 500,000 entries. And also, we formatted the data visualizations in order to fit our data visualization management system. And for future work, we could research new ways of visualizing this data in order to reveal any other interesting patterns. And we could also simplify our user interface in order to make the user interface more easy to use.
Yeah,
We would like to thank Ken Allen for the idea of the project, Richard Julich for instructing us and helping us in any way he can, and Graceland as well for the same reasons Richard Julich. Thank you for your time.
Yep, thank you.